Hey everyone, this is Daniel for Rock the Code, and in this episode, my guest is Daniel Spiewak. He's known in the Scala ecosystem for leading the effort of Cat's Effect, one of the major Scala effect systems used in production at big companies in critical systems. And Daniel now works at NVidia as a distinguished engineer. And in this conversation, we cover many things about Scala effect systems, of course, his open source work, his work at NVIDIA, what it means to be a distinguished engineer or what it means to become one, and a lot more. So without further ado, please welcome Daniel Spiewak. Daniel, it's good to have you.
It's really good to be here. I'm honestly a big fan.
Thank you. I am honestly a big fan of your work as well. And what better place to start than Cat's Effect, of course. You just released 3.7, and this brings proper multi-threading support for Scala Native. Why
Mhm.
is that a big deal, and why is Scala Native a big deal?
Both of these are awesome questions. So let's talk about what multi-threading support actually means. So Cat's Effect has been running on Scala Native for a while now, Scala Native 0.4. And kind of famously, Scala Native 0.4 uses the same threading model as Scala JS, which is the JavaScript threading model. So you've got a single thread, and that's all you work with. Now, just like with Scala JS, Cat's Effect works just fine with that. You can have fibers, you can have like multiple things kind of running and concurrently, like all that type of stuff. But you of course can't saturate more than a single CPU core, and there's other drawbacks that you have to be aware of. But Cat's Effect does work just fine in that context. Um, what Scala Native 0.5 adds is native support in the underlying runtime for accessing pthreads, which is sort of the abstraction for actually interacting with the kernel. And then all of the downstream implications of that are handled, right? So you have to have a garbage collector that now kind of understands multiple threads referencing things, which is immensely complicated. You have to have a memory model, which talks about like, well, if I write some data on this core and then I read that data from this core, like how does that work? And like what guarantees do we have or not have? So Scala Native had to figure out all of that and implement that in 0.5, which is a monumental task. Like really kudos to the team for doing that. But once they've done it, that brings Scala Native's runtime sort of speed of light, basically, into the same ballpark as the JVM, right? I'm not claiming that performance is at parity. Performance is a very, very complicated topic here, but it at least means that if you have a machine that has 32 cores or something like that, a Scala native application can now use all 32 of them the same way that a JVM application would. And what Cat's Effect 3.7 does is it basically ports all of the machinery that we've been building on Scala or on Scala JVM, basically, ports that to Scala native. So all of that is now cross-compiled and shared. So we've got the work stealing runtime, we've got like all of the concurrent queues and things like that. Like basically all of that machinery, everything about how fibers behave is ported over. The trick though is that's not really enough um, because the concurrency, especially in a and parallelism, especially in a framework like Cat's Effect, is really only useful if you can access I/O and actually do like multiple sort of sockets in parallel and read from multiple files in parallel and things like that. When you really boil it down, if you don't have that ability, then it's kind of pointless. And on the JVM, we inherit that ability generally from the broader JVM ecosystem. Now, there's an asterisk on this. We'll come back to that, but like the broader JVM ecosystem being like, Java.io, Java.nio, in some cases Netty, like, we'll talk about this more, I'm sure, but, we have something that we can sit on that sort of understands threads and you can use sockets across them and like all of that sort of works. And then asynchronous IO works within that context. None of that actually exists on Scala Native because in a sense, Scala Native is like much, much, much lower level. So, I mean, they have ports of Java IO stuff, but it's pretty direct, basically. Like it doesn't have this same type of integration. So what we actually had to do was not only port the threading runtime, but we also had to create an abstraction which allowed us to effectively replace the entirety of Java NIO. Like really all of the underlying asynchronous IO substrate that you sort of take for granted on the JVM, we had to build our own version of that. Now, there were other reasons to build our own version of that we sort of explored in previous releases, but like we knew that we were going to have to do this, so that kind of set us on this pathway. So this has been a many, many year journey. Multiple releases of Cat's Effect have been building towards this because we knew we had to have this piece in place. And that allowed us to write implementations that were specific to Linux with the epoll function, specific to macOS and BSD with the KQ function. We have a fallback that sort of uses other things, and that we even have an experimental runtime that uses IOU ring. So these are sort of the asynchronous I/O substrates, which have to be then married to the basically the fiber scheduler and the fiber runtime in order to make any of this stuff useful. So we had to do all of that stuff, and that was very challenging because there's not, like, you're working with a layer of the kernel that like very, very few projects actually touch. So we sort of did all of that, and then now it's released, and this together with the fact that we went and carried this through the entire ecosystem, especially FS2 and HTTP4S and Ember and Skunk and things like that, this basically means that if you're writing an application that's using sort of a fully quote unquote native type level stack, sort of top to bottom, then chances are really, really good that you can just compile it and run it on a JVM or compile it and run it on LLVM exactly the same. And then you get the different benefits of the LLVM runtime that are a little bit different of a trade-off space than the JVM, but without sacrificing the fundamental performance constraints.
Why all this effort? Because that seems like a monumental thing to re-implement pieces that you take for granted on the JVM and put it on Scala Native.
Yeah, I think there's two sides to that. So there's benefits that Scala Native brings to Scala, and I think there's benefits that supporting Scala Native brings to people using Scala on the JVM. So I'll do the second one first. So as we started thinking along these lines and thinking about this problem space, we realized we were going to need this to make Scala Native work, and it kind of like put some ideas in our head. And that was what got us on the path of what we now call the integrated runtime. And so not only do we replace Java NIO on Scala Native, we also replace it on the JVM. And it turns out that doing that is actually super beneficial for performance on the JVM because it makes the thread scheduler be in charge of the syscall boundary. So let's take a step back really quickly. On the JVM, we've had multi-threading basically since Java 1.1. I think it was 1.1. It might have been 1.2. Either way, like Java got real threads at some point very, very early on, right? And we've had that, and we've sort of leaned on that, but we haven't been using them with asynchronous patterns. So multi-threading kind of ran ahead of that in a sense, which meant that the JVM ecosystem evolved in this very, very strange way, where people sort of write multi-threaded applications, sometimes with thread pools, sometimes with futures or whatever like that, and then they sort of interact with IO layers, which kind of export these sorts of interfaces and runtimes, which then internally are reliant on dispatcher thread pools that sort of ultimately talk to the kernel. And by the way, talking to the kernel is very, very expensive, so you want to be careful about it. But that you just have an event dispatch loop or something like that, like one thread, two threads, four threads, whatever, that are sort of reading events from the runtime and then pass that over, and now you've got your futures over here. That's how everything on the JVM traditionally works. If you tell this to someone who is familiar with another ecosystem, especially if they're familiar with C++ or C, but even something like Rust or Go, this probably sounds bizarre. Why would you do it this way? Because the way that every other language ecosystem does it is they merge these things together. Why would you have your user space code over here running on this thread pool, and then you're talking to the kernel on this thread pool, and that's the only thing the thread pool does? That's very, very odd. Generally what you want to do is you want to put these things together, and then you have a little state machine that talks to the kernel within each thread. That's how everybody does it. What we did with the integrated runtime is we made Cat's effect work in that way. So it basically pulls the syscall boundary into the scheduler. So now the scheduler basically is aware of when you're talking to the kernel, and then when you talk to the kernel, it tells the kernel how long it wants the kernel to wait, and so it integrates the timers and the IO and all of that. And this, especially for certain workloads, brings really substantial benefits performance-wise to the JVM. It also allows us to take advantage of stuff like IOU ring, which otherwise we really wouldn't be able to do. We have a more optimized implementation of using epoll, which is something that is sort of famously terrible when you're using it with selector on the JVM. So stuff like that, right? We're just able to do better than the JVM can do, and you get much better results. So that's bucket of benefits number one, is basically we started thinking about Scala Native, and then we sort of carried that thought process into the JVM, and we realized, holy crap, we could just make the world a better place, even if you don't care about Scala Native, right? So that's thing number one. But then thing number two, Scala Native by itself is actually in a really interesting technological space right now. So let's take a step back and talk about the macro picture of the universe, right? Um, the JVM is 30 years old. Like it's really old. Now it's excellent technology. It's very good at what it does. But in a lot of ways, the JVM and many things on the JVM were designed for a different era of software, an era of software in which everything was very CPU oriented. Your RPS per node was probably hundreds, not tens of thousands. You probably had one or at most two CPU cores, and you were probably deploying on like a big monolithic application server that just ran on some bare metal hardware. You didn't scale horizontally very much, and like that was just how the world worked. Um, the world hasn't worked that way in 15 years, right? And now we have very small containerized applications that we put into Kubernetes. We use things like Lambda and cloud functions and things like that. Many applications are now both CPU and GPU, and or even TPU, or eventually quantum processors. Like there's a lot of like very bespoke things that kind of go on in these layers. Startup time starts to matter as you're sort of auto scaling out when you have load spikes. Memory footprint starts to matter in ways that the JVM ecosystem is not very compatible with. So there's a lot of this sort of stuff which just starts to be like, eh. And I think in a way, the fact that the JVM is not very good at this stuff. I mean, it didn't even understand C groups until like, what was it, like Java 17 or something like that, right? Which is insane. So the fact that the JVM is not particularly good at like working in this sort of cloud native environment, like modern cloud applications, it's kind of like a poor fit for that in some ways. I think that's actually been one of the things that has juiced the rise of other language ecosystems, like initially Node.js, which is quite good at some of these things, but also Go, right? And like Golang is very popular in this exact problem space, where ostensibly the JVM actually is also quite good, but like Go just has a different set of trade-offs, like statically linked binaries. So um, what Scala Native does is it allows you to use Scala with all of the benefits that the JVM is like quite bad at. So now you can do a statically linked binary, which starts instantaneously, which you could put inside of a container and like give it a very small amount of resources and it works super fine. Like you have native bindings across the ABI without the overhead of JNI and without the overhead of Seago, by the way. So like you're really going about as fast as Rust goes from that standpoint. And so you can do things on the GPU, you can do things on TPU, and like other places where you actually need to make these sorts of native calls. All of that becomes possible in a way that it isn't possible on the JVM, just kind of in a fundamental way. Now you give up other stuff, right? Like to be clear, LLVM is not like a panacea. There's things that the JVM is just always going to be better at, especially like long-lived garbage collection. But you don't have to pick anymore, right? And then with stuff like Cats Effect 3.7, like you can really kind of swap back and forth seamlessly, or even have an application which runs, compiles and runs in sort of both environments. So it puts Scala and more broadly the Typelevel ecosystem on roughly level playing field with the Rust ecosystem, which is the only other real contender in this space. And that's kind of remarkable.
What chances do you give Scala Native to contend with Rust in this space, given the enormous amount of resources and the enormous amount of attention that goes into Rust compared to Scala Native?
Um, I mean, that's hard. And there's a lot of factors here, right? Like I've been following alternative languages for a really long time. And so, anybody who's done that understands that like the factors which influence the success and adoption of a language are usually not how cool the type system is, right? Or anything like that. So, there's a lot of things that are going on right now. So let's kind of take a step back, right? So Rust has been going for a while now. It's older than everybody remembers it is for some reason. It does have a very mature ecosystem. Um, it has a really high learning curve that puts off a lot of people. And it has a tendency to make very easy things difficult sometimes, which also puts off a lot of people. So, when I hear complaints about Rust, that's the thing I tend to hear complaints about. So that kind of has held back Rust for a long time. A lot of people who have those feelings end up in Go because those same people will have a very similar set of complaints about Scala, right? It's like, oh, implicits are confusing and you use underscore for everything and like, ew, JVM, right? Like, stuff like that, right? I hear that all the time. Um, I think it is, if we were sort of in a classical world prior to sort of the advent of more modern tooling, which we'll talk about in a second, I think that those factors would kind of dominate. And a lot of people would maybe not even choose either of them. They'd just be like, yeah, Go is fine, right? Like, which people did for a long time. Um, Now that we're in a world of agentic coding, a lot of those sort of syntactic biases go by the wayside, right? Like the model doesn't care about like pedantically fiddling about the borrow checker in order to get a print line to work, right? Like it'll just like do whatever boilerplate is necessary. So like those disadvantages of Rust go away. Um, Conversely, the model also doesn't care about like all of the craziness of like, getting implicit scoping just right and like, having the types line up in like these really convoluted ways that Scala sometimes makes you do. Like the models are very, very, very good at that, especially with the help of the LSPs. So really at some point it comes down to ecosystem strength and the biases of people doing the technical selection. So I think that right now it isn't broadly known within the industry what Scala Native can do. It's actually very, very niche. Like I have a colleague of mine who's at NVidia who was in the Scala ecosystem for a really, really long time. Like, and he wrote a book right, like in the Scala ecosystem. Um, but he's been out of it for like a little while, and he didn't even know that Scala Native existed. So like if someone who was so deeply plugged in for so long and then has only just kind of been out of it for a little while, if that type of person doesn't even know, then like 90% of everybody else isn't going to. So if that state of affairs continues, then unfortunately the answer to your question is yeah, Rust is going to win. Like because nobody knows that Scala Native exists.
What would be some decisions or some actions that the very small Scala native team can make or take, depending on what you decide on doing, uh, to popularize Scala native sustainably in such a, I don't know, resource constrained environment? I mean,
Mhm.
there has to be something that is disproportionately effective in that way. Do you have anything in mind?
Um, You have to show it working. You have to show it doing really good things. And you're not going to be able to show it doing something that Rust can't do because it really occupies the exact same trade-off space. But what you can do is you can show it doing the things that Rust does very easily. You can't, so, here's some command line tooling, here's some things that like bundles up into here's a service that we bundled up into a container and statically linked here, and we scaled up and down really easily. I think there was a proof of concept for a while that like Virtus was working on where Scala CLI was really tightly integrated with AWS Lambda. So it was like super easy to like write a Lambda like basically in the CLI and then deploy it. Stuff like that actually be awesome. I'd love to see more things in that direction. I think a lot of people probably would love to see more stuff in that direction because it makes deployment very, very straightforward. Um, I think another area that I've been exploring more, and I think we actually have a Summer of Code project for this under Typelevel, is basically exploring Onyx integration and the Onyx runtime, which is something that's sort of very uniquely in a native layer. Now, Rust can do this with natural bindings as well, but like, showing how you can have like basically very, very fast sort of speed of light model performance referenced from an application written in Scala and then reach out for the richness of the Scala ecosystem that you already have, like that's actually kind of pretty compelling. Again, like you could sort of pragmatically say like, well, Rust can do that too, and that's true, but like showing that this happens starts to put it more and more on even playing field. And then you can start to bring about the things that are more uniquely Scala, right? For example, Scala.js exists. So you can have that sort of that dream that like, Ryan Dahl used to talk about with like Node.js, where like you write your whole application in a single language, front end and back end. Well, Scala is one of the few languages where you can do that. Rust compiles to WASM, but it doesn't as far as I know, it doesn't have a very good JavaScript mode. So like, the the strength that we have in Scala is that we can kind of cut across that boundary really easily. So you can start showing that type of stuff, but like I think you have to start by basically showing that it exists and it can do the things that people are trying to do it without the JVM, do it, have this sort of native access across the ABI boundaries, like just really talk up the strengths of the runtime. So that has to happen.
And on a broad, say on a much broader scale, you talked about the fact that agentic development changes the discussion about the usual comparison that we tend to make between languages, between tooling, between library
Mhm.
stacks, between the bedrock, be it the JVM or native or whatever that is. How should Scala position itself for agentic AI, and what are some of the tools that you think would be very beneficial and make a lot of difference with, again, minimal effort and with say, manpower constrained environment?
Yeah, of course. Um, Couple of thoughts on that front. So first off, let's talk about what makes agentic programming good, right? Like what is like an effective way of using agentic tooling. So these are stochastic machines. They're very, very good at generating code, but they have a tendency to kind of go wild. And hallucination is less of a problem than people think it is, but just not doing the right thing because maybe your specification was ambiguous is very, very common. Um, you know, things just being weird. So the key to using these tools effectively, and this is not a novel observation, is you kind of always want to put them into a little box so that they can jitter around inside that box and like the implementation could be whatever you want, but like your API signatures and your type signatures and like your sort of modularity boundaries and like all of that stuff, you sort of pre-decided that, right? You sort of specified the tests or whatever, so it kind of doesn't matter what happened inside of it. When you do that, they're actually very good at like getting something fairly optimal inside of the box, usually. Um, and you can do this with different size boxes and put your boxes together. And now here's how you actually write code using tools like Codex or Cloud Code. Um, so the when that comes down, when we think about languages then, and when we think about ecosystems, um, that means that the absolute top bit that you need to achieve is you need to make it very, very easy to put languages in a type box and then review the nature of that box as a human being. So that means, generally speaking, obviously like unit tests and having a unit test ecosystem and things like that. This is table stakes, but more importantly, you need to have a very, very strong type system. You need to have a type system that's very expressive, that like users can kind of say things in parametric ways. Ironically, things like functional programming become incredibly important techniques because again, it's just like, let's build these really, really tight boundaries and then like the agent can kind of live inside of that. You can only have so many implementations of like this type of function. So there you go. So you want to do this, you want to do it in a way which is human reviewable to the extent that it needs to be. Reviewing Java and Go type signatures is absolutely miserable and lossy. Reviewing Rust and Scala type signatures is actually kind of fun. So like, basically those two languages work really well for this type of thing. And you need to have tooling that like exposes this in a very rich way, ideally more than syntactic, to the LLM. So that means Scala metals, it means like Rust analyze in the case of Rust. Like basically the LSPs become really, really important. And that's how the sort of agent ends up iterating. I've certainly personally experienced this, right? I've sort of done tests where I've done like, written code, with and without the LSP enabled and like sort of seen what it does in multiple languages. I've had colleagues who've done this, things like that. And really the LSP and the strength and richness of the type system that it's able to feed back is absolutely crucial. Like it makes such a difference in like the quality of the code that churns out, the minimizing the number of tokens that's required to do it, et cetera, et cetera, et cetera. So there's nothing that can be done that is as impactful as that. So we're already in good shape, right? Like, Scala is super good at that. The Scala ecosystem exploits the type system very well. Like it's, there's especially the functional programming side of it, like really is already in this bucket. So, Scala metals can always be better, but it's good, right? It's already good enough that it's like providing a lot of value here. So that's kind of one thing. And then, better compiler errors is always good, and it helps the models just as much as it helps humans. I think the second kind of tactical thing is it's one of the strengths of Scala is the ecosystem that it sits on top of. Um, the Scala native ecosystem as well as the JVM ecosystem as a whole. And agents are generally pretty good at like leveraging that stuff. And they solve like a problem of discoverability where it's like really difficult. Like I just need an HTTP library to like fetch this thing. Like what do I do? Well, that's always been a problem because there are so many options. Agents are good at kind of breaking that deadlock, but the problem is that they quickly end up needing to figure out things about the libraries they're touching and the APIs they're touching and things like that. And they'll usually fall into a couple of really terrible and inefficient traps for doing it. So, they'll look at what the LSP feeds them back, but something in their fine tuning, they understand that the LSPs are often stale and like don't give them all the documentation. So really what they'll often do is they'll go get the source code from somewhere like Maven Central. They'll like inflate the jar. They'll start reading the source code of like some library that you're using. They'll generate Java doc for themselves, then like parse through that. So I actually think that now this is actually one area where Go has really, really, really good tooling because like Go, you can basically just ask for like, give me the documentation of any like public unit and it just like feeds it back to you, whether it's like on your local system or in, in the Go proxy, the Golang proxy. Stuff like that would actually be really, 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 really helpful. It doesn't even have to be an LSP. It just has to be like, Scala CLI docs fetch or something like that, right? So this type of tooling where you're just kind of giving back very tailored information to the models is actually really good. Anthropic has a term for this called it's like a progressive disclosure, where like basically what you always want to do is like give the model like a tiny little bit of information, which it can use to decide does it want more information. Then give it a slightly bigger version, like more verbose version of that information. It can use to decide does it want more, right? Like that type of a thing. Giving it a whole Java doc index.html is like giving it everything at once, but like giving it the ability to say like, oh, I want this compilation unit. I want to know more about it. Okay, here's the header, like that type of thing. Scala can do a lot better on that. Like we have Maven. Maven is awesome. It is so good. Like that would actually like catapult things a lot further. And then as kind of coming back to brass tacks, as people start to realize that they're just getting better quality code out of agentic tools and they're getting more of it and they're getting faster because of these little things that we're doing, like that builds a network effect very quickly.
Do you have an example of a an actual particular tool that you think would be improved? Because what I'm hearing from you is that Scala is great at the for its type system, which I definitely agree. We have a lot of things right. We have a rich ecosystem of libraries and stuff that is also easily centralizable, easily searchable, and so on and so forth. What are some examples where it's specifically lacking? Like, give it like a concrete, like this library sucks because such and such, and this is how it would be much better for agentic tooling, and in this case, it would make Scala development much easier and safer at the same time with AI.
Yeah. Um, I will pick on three examples here. So first off, from a tooling standpoint, I really do believe we can do better at like the docs exploration. We should just copy what Go does because like the Go like doc perusal tooling is just really, 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 really good. So we should have that. We can have that. That's not even a high bar. So let's say we have that. I think from a tooling standpoint, actually, like we're pretty good at that point. Second example that I want to pick on. Scala very famously has a lot of stylistic differences. And this doesn't confuse the models as much as people think it does, because most of what the model does is very syntactically agnostic, but it does mean that you're going to get output Scala, which is really highly heterogeneous in a way that a human being wouldn't produce it. And that can have consequences, right? Like when I've tried to write Scala using like Claude, for example, even when I tell it to do things in a very functional style, I'll frequently get early returns and other weird things that like I would never write and no one would ever write. Like it's very unidiomatic. You'll get weird mixtures of like braceless and brace style, like stuff like that. And that's just like crude. So I think something that would actually probably be helpful is like kind of a strict mode for Scala 3 in some sense. Like, thou shalt only use braceless, right? And like maybe you only use that when you're writing agentic code. It's fine, no one cares. But like having the ability to toggle that on in the build, that would be probably good. But it is more of in a sense, it's almost more of like a ecosystem problem. Like as a community, in 15 years, we've never settled on one style of Scala. We fought bitterly about it. So it's a hard genie to put back in the bottle. And it is one area where Go and Rust are just like head and shoulders above us because they do have a very, very uniform style of writing things by design. So we can work on that. And I think some of it's tooling, some of it's culture. Like I think we can kind of push on that. On a library side, though, I'm actually going to pick on FS2 and Cats Effect because I feel like that's fair. So when I've written code using models which touch those libraries, it tends to do pretty well, and especially in the areas where it's like where you're able to express very robust things with the type system and other things like that. It's definitely a thing that it does really well. It generalizes its knowledge of stream processing and I/O and asynchronous I/O really, really well from other language ecosystems to Scala, so that's good. But what it doesn't understand, interestingly, is resource life cycles. And I think this actually says something kind of interestingly profound about the difference between humans writing code and models writing code. So for those of you who are maybe unfamiliar, the Typelevel ecosystem and Cats Effect and FS2 in particular have always had a very particular bias about how resource management should work, right? So whether you're working with Bare IO or you're working with FS2 Stream or whatever it happens to be, there's a built-in notion of finalizers and resource scoping. So when you acquire a resource, you generally say that you're going to, how you're going to release it, and then the runtime takes care of making sure that that happens no matter what, regardless of whether you're errored or canceled or completed normally. And there's a lot of trickiness around that. So it's very, very nice. The emperor has no clothes part of this is it's all been a syntactic trick from the beginning. Like from the very, very beginning, it's just basically been API design that really encourages people to use the resource type because the resource type is good and it's very convenient. And when you create a resource, it encourages you to do that. And when you use the resource type, don't touch allocated, right? And don't use really, just stay in resource. It's good for you. When you use stream, stay in stream, don't call .compile, .compile at the end of the world, right? That's just kind of what the API has carroted people to do, what the examples carrot people to do, what the discords carrot people to do, but it's all a trick because, .allocated is always there with resource. You can always use into pure and then just escape, right? You can do analogous things with stream, especially if you're compiling. There's a lot of sort of subtle and also not so subtle implications of this. One of the subtle ones that I like to talk about is there's a difference between resource scopes that get extended by flat map. So it's you flat map on the thing and the resource gets pushed down versus resource scopes that flat map goes on the outside of, right? It's kind of an associativity problem. I call this static versus dynamic scoping. Models manifestly do not understand the difference between this. So they're constantly messing it up, and then you're not going to actually figure it out until runtime when you have a resource leak. So of course the model can't see it because it can't, it's not going to be in the tests and it's not in the type system, which kind of brings us back to actually what we can concretely do about this, right? It's interesting that this sort of syntactic trick has worked so well on humans for so long when really all it is kind of like a paper door. The models just barge through that paper door again and again, and they don't care. So this is actually one area where the Typelevel ecosystem needs some work. right? Um, but the key thing is it needs some work in cooperation with the language, because there's a reason this has been a paper door all this time. And it's because linear logic is not embeddable within predicate calculus. And so then by the Curry-Howard isomorphism, if you have a type system which is primarily predicate calculus, which is what Scala's is, then you cannot express linearity without additional language features, right? So we have no notion of borrowing, we have no notion of alias checking, like none of that can be encoded in Scala without additional language work. So that meant that at the end of the day, we can't actually like prevent people from leaking resources. Just fundamentally, you can prove that we can't prevent people. So it had to be a paper door. So I think you know exactly where I'm going with this then.
Uh, I'll let you continue.
Okay. Well, capabilities
Yes.
has been an area of research for a while.
And Martin
And
is
yeah.
very proud of the work that went into capture checking and capabilities.
Mhm.
Um, Tell me where you want to go with this and how you want to embed that into the example that you just described.
So capture checking is basically kind of a form of borrow checking, a form of alias checking. It is formally speaking, it is a linearity feature. It's actually an extension of linearity, so it's like broader than that. Um, and it brings the ability for us to forbid things like resource allocated, or at least force people to say in the type system that they are okay with this being a thing. Um, so in Rust, for example, you have an unsafe block where you can just kind of YOLO inside of it, right? Like stuff like that is kind of what I'm thinking about. And it really, really is rooted in the type system enabling that. Now, it does add a lot more complexity to the type system, and especially for signatures like stream and resource, you can imagine how crazy it's going to get very quickly. But the models don't care. Like they don't care as long as the type system is parsable, right? And as long as it can, the errors are comprehensible and actionable, and it gets expressed to it in a semantic way. Like it really doesn't care how convoluted the types are. It's going to piece it together. So, um, like capture checking is awesome. It's really, really awesome. And I think that it's one of the few major changes to the Scala language that's sort of being proposed that I actually think would meaningfully improve Scala's market share. Because like once that happens, and then you get the ecosystem to start to leverage it, which that's also going to be hard. So we're going to have to figure out how to do that in a way that's just backwards compatible. But like you get the ecosystem start to leverage it, um, that's where you close this hole, right? And then suddenly the ecosystem becomes more reasonably usable and more safely usable.
Now, because we are in the agentic development territory, I wanted to ask you about your current work at NVidia.
Yeah,
Um, to the degree that you can describe it, what are you currently working on?
yeah, I can talk about the technical sides of this all day, which is really nice. So stop me if I ramble. So I'm working in robotics. I'm working on autonomous vehicles, actually. A lot of people forget this, but NVIDIA has been working in automotive for a really long time, and we started a proper AV program many years ago. We work with a number of different partner companies. You can actually, if you buy a Mercedes-Benz now, like certain models of that actually have our hardware and our software inside of it, and the autonomous driving features inside of those cars. Like that's the project that I work on. So I work specifically on the infrastructural side of this. So infrastructure in this sense basically means a lot of the data infrastructure, the tooling, the cloud side work, simulation, platforms, like stuff like that. And this is it's a really, really big and complicated problem space. Like building an AV is hard. Like however hard you think it is, it's much harder than that. So you need to do a lot of very, very convoluted things at extremely high scale, like hundreds and hundreds and hundreds and hundreds of petabytes of data. You have to deal with video at like really, really high scale. LiDAR is awful. Nobody likes it. Like, and you have to deal with very, very complex structured logging. You have to understand sort of training life cycles. It's like, oh, okay, well, this model is reading sort of using camera data to infer static geometries of like road boundaries and lane connectedness. So like it's going to need to be trained in this sort of way. You have to figure out, and I'll come back to this in a second, but like you need to When you're thinking about this from an infrastructural standpoint and a framework standpoint, which is the space that I work in, you you need to start by sort of understanding the full problem, like how is it you actually make the car drive itself and what are the pieces involved in that and how does the on-vehicle part. You have to kind of understand all of that and understand it from sort of soup to nuts, like how do the machine learning engineers work and like how many tens of thousands of GPUs are they going to need to like train this next iteration of their policy models? How many parameters does it have? What do those parameters mean? Like you actually need to understand all of that stuff in order to work it backwards to like, well, in order to curate data for your next training run of this end-to-end model that like spits out trajectories and drives the car, like you're going to need to curate data using these attributes. So these attributes we can get them by like running these sorts of models in the cloud and like generating metadata. We can store this metadata in certain ways. Like you have to kind of really decompose the problem like that. And that is a very, very challenging full stack, broad organizational problem.
And what are you using for this sort of large scale infrastructure? This sounds like a large, I mean, okay, there's a lot of complexity around this. Okay, just naming it a distributed system just probably
Mhm.
is an oversimplification by orders of magnitude. But what are you using to make this thing real, and what are some difficult parts about it?
Yeah, so I'll spoiler right away and say that we're not using Scala, which is unfortunate. I actually think that parts of it and parts of the org actually would be much, much better off if they were written in Scala and just running the JVM. But like that's a different argument for a different day. The so the on-vehicle part of it is written in C++. That's probably not surprising. I mean, this is stuff that has to be safety certified. It's kind of like writing code for the space shuttle, right? Like I mean, it's like really, really very pedantic, except if the code for the space shuttle had to do like tensor encoding of geometries, which is like not an easy thing to safety certify. Um, a lot of the semantical code, like the business critical code that deals with data mining or curation or auto labeling or certainly the model training and things like that, that's all Python. Um, uh, there's bits of it which kind of cut across. So like people will write a lot of it in C++ and then bind it into Python because you sort of have this problem where like your inference on vehicle has to be C++. We're not putting Python in people's cars. We're not insane. Um, but then you've got to actually run inference in the cloud when you're doing training because inference is part of training. So then you have to, how do you do that? And then it's PyTorch versus TensorRT and like et cetera, et cetera. So a lot of complexity there. The cloud side of it, like the bits that things like robotics log analysis, where you're like looking at a segment of time and you want to see all the cameras and all those sort of track lines and obstacles in free space and things like that. If you're doing that type of thing, the backend for it is written in Go. And like a lot of data processing, a lot of the orchestration around data pipelines, that's primarily written in Go, though there is an increasing amount of it written in Rust as well.
What are some challenges that you see? Are you overseeing this whole thing? What is your current role in this whole system?
Uh, so my role is I work across kind of all of the teams. Nobody reports to me. I'm not like a manager, but I basically go around and I have to kind of understand how everything works. I think quite a lot about where things have to go. So you think about sort of architectural things and things like that. I'll go down very much into the nitty-gritty details sometimes. Like I mean, I'm working on a pull request right now, which is sort of re-architecting some of the core abstractions in the implementation of our high-scale simulation system. Because I happen to know that that team is struggling with certain problem spaces, and that's creating like resiliency problems, which in turn is creating like program level like issues where it's not as reliable as that. So I'm going in and I'm like basically redoing some of their core interfaces and making it more testable and things like that. So I do a bunch of that type of stuff. I also do stuff. I kind of take this and I go broader within NVIDIA as well. So like our organization actually is chartered with all of physical AI. So we also work on other robotics programs, like, very, very famously NVIDIA is making humanoid robots now. So I work with those folks and like, I try to see how it is that we can build the machine that makes the machine in a more general sense. So there's other people who do this with me. I'm not the only one doing this, but like I try to kind of have that very broad view. Most people, because they're so focused on their kind of day to day and so in the weeds of their very specific problem space, it's hard for them to know like, oh, okay, this is what the other teams are doing. This is what the other programs are doing, the other parts of NVIDIA. Like I have to kind of keep track of all of that.
Uh, if I scanned your profile correctly, your position is called distinguished engineer.
Mhm.
What does that mean, and how does one become a distinguished engineer?
Um, yeah, so titles are, varyingly meaningless. It
I
basically,
mean, distinguished engineer is probably one level below like technical fellow, and which is reserved for
yes.
the probably highest researchers and whatnot. I spoke to Simon Peyton Jones the other day, who is a research fellow at Epic. So
Mhm.
those kinds of folks. What does that mean? I mean, titles aside, but the role
Right, right.
specifically.
So this kind of gets into like standard tech career ladder stuff, right? And almost every company that isn't Google has a pretty uniform model on this. Google is similar, except it has another rung because they just wanted to be weird. I don't know. But like almost everybody has the same kind of rungs. So if you're sort of an IC1 or an IC2, that's kind of like an associate or a junior engineer, right? Like you're just out of college, you were just hired, like you're going to be that for a year or two or something like that. And at that level of granularity, you're expected to be able to work on like a single task, but with a lot of help, right? You're a junior engineer. Senior engineer is IC3. So this is where you should be able to work on a task by yourself. Maybe you can even break down something into tasks semi-autonomously. Like you kind of start to formulate a vision for the future. But you're not like leading a team, you're not guiding lots of people, you're not like influencing broadly across the organization, and you're not expected to kind of see beyond the project that you're working on. You don't have to contextualize that. Um, IC4 is lead engineer. So lead engineer is where you're influencing the whole team. Now you're spending somewhat less time coding. Maybe you have to know a little bit about not just your project, but the projects around you, maybe a little bit about the business requirements on you and like why that is the case. But you're still pretty hands-on, like you're still pretty in the weeds. And there's loads of stuff that maybe you wouldn't be able to do yourself, right? Like if someone comes to you and says, make the car drive itself, you're not expected to be able to do that, right? Like so then you kind of, and as you keep laddering up, we kind of keep generalizing in this way. So IC5 is staff engineer. So staff engineer, you're working across multiple teams. Now you're really writing a lot less code because you just don't have time. You're carrying context around between people. You're expected to really kind of understand how these teams work. It is a technical role. It is an engineering job, but you're now starting to think more about people. And you're like, oh, okay, well, I love this architectural idea that I have, and definitely the modularity should be broken down like this. But that would mean that like these two guys over there would have to like handle this degree of complexity, and I happen to know that this one's really bad at like this system, and like this one has these like proclivities, so I'm going to re-architect it like this so that I avoid their weaknesses and play to their strengths. You start having to have those types of things at staff level. Principal level is like that, but one more up. And now at this point, your staff engineer maybe deals with many dozens of people, like maybe 30 people or so in their umbrella. Principal engineer, now you're getting to like 100, 150, 200 people that you're kind of, this is your umbrella of scope, where you're kind of looking at all of them, contextualize all that together. You need to have a deep understanding of the business and like, why are we doing the things we're doing? Why does it matter to NVIDIA's bottom line that like we're making the car drive itself? Like, can we answer that question and like, can we do it succinctly? You need to be able to like work with executives and like VPs and things like that. Like principal is like very, very, very senior. Um, Distinguished engineer is IC7, and that's like one level up from that. So now instead of hundreds, maybe you're dealing with thousands, right? Like, and maybe you don't deal with thousands of people every day. Like that's just too much for any one person, but you certainly have to understand that whole space. Like I was talking about, for example, I need to really know like how does the on-vehicle stack work? Right? Like, how do you do scheduling in a safety critical environment where you have to produce a new trajectory like 10 times a second? Like, what does that actually mean? How did I know that it was 10 times a second, not 15, not 5, right? I've got to know that, and I've got to know what that means for everything. What is machine learning? How does that work? What is the future of data curation, right? Like all of that stuff I kind of have to think about. So that's distinguished engineer, and you're really you're covering a very, very broad space at this point. But really, it's that same idea. We're just laddering out the same skill set that you have as a senior engineer or a lead engineer. Now you're just doing it over a whole organization, like large part of a company. Engineering fellow is that, but now really for the whole company. So like if you're a fellow, you probably invented the GPU, like, and that's IC8 basically.
How does one progress to a distinguished engineer, and certainly as fast as you have, because these titles like distinguished engineer, fellows, you name them, like senior staff, whatever the titles are, they revolve around the same kind of space. Uh,
hmm
with enough context across large swaths of code, large swaths of teams and stuff like that.
hmm
But these titles and these roles are generally reserved for gray beards and gray hairs and stuff. How does one get enough context or enough understanding to be able to operate at that level?
Um, a lot of it is experience, right? So this is why it does tend to be older folks because it at some point it's very difficult to just have enough exposure without having enough time, right? In some sense, the human brain only works so fast, right? And you can sort of adapt to new things. Um, a lot of a lot of tech is more uniform than people think. Like there's only really a small set of core problems, and if you just sort of repurpose those problems, you can kind of almost solve anything. Even just making that observation, though, requires a lot of exposure to a lot of different problems. So one of the things I've been very fortunate about in my career, and I swear I didn't set out to do this, it just sort of happened, is I have worked on a lot of very, very different things. Like I've done a lot of very, very different stuff. I've been really lucky in that. Like a lot of people have been willing to take a chance on me. Like with NVIDIA, for example, like I had never worked in robotics before when they hired me, and they were just like confident that I could learn it. So now I've worked in robotics, which is like totally different than working in large scale distributed systems and databases and file systems and like all this stuff, right? So you need to kind of like see a lot of different stuff. You from a technical standpoint, it's really about breadth, not about depth. And I think this is even more true in the agentic world, where like you can be as deep as you want to be by just like talking to Claude, but like being broad, that's where the models flip out because they can't really help you like navigate that space. So human judgment matters a lot in breadth. Um, so you need to build that up. You need to have a couple of areas where you are very, very deep and kind of go all the way down to the middle and like, prove that you can do that. Um, and you need to be able to communicate. You need to be able to work with people. Um, at the end of the day, while this is engineering, right, it's still that same skill set of like looking at a problem, looking at its constraints, breaking it down into like composable pieces. That's engineering, regardless of what the pieces are, right? Um, but when you're doing it at such a large scale, you're doing it with human beings. You're doing it with longer time scales. And so you have to like be very, very good at writing, be very good at presenting, be completely okay, like going up in a whiteboard and like a senior VP is angry with you and like you're like explaining to them this like very detailed thing that they shouldn't have to care about, but for some reason it's making the product late by several months. Like you've got to be able to do that. Um, and so you sort of build your presentation skills, build your communication skills, build your human skills, like interact with human beings, meet them where they're at, like invest in human beings, and get that breadth of experience.
I mean, maybe it's a connected question, but while you're working on Cat's Effect, at least, I mean, across many things that you've worked on, you went on record I mean, in your conference talks and such,
Mhm.
you spoke about both very high levels of abstraction and very high level concepts and type classes and very high level up, and
Mhm.
also very deeply close to the bare metal,
Yeah.
chasing microseconds and stuff. I mean, this is pretty rare in the sense that I mean, programmers that I've spoken to either chase one end of the spectrum, either very high levels of abstraction and not caring about performance too much, or very performance oriented, very close to the bare metal, very aware of every kilobyte, of every line of cache, and stuff like that. But you've managed to hold both in your mind to a very high level of performance, as far as I can tell, especially when it comes to the work that you've produced that is public. How have you managed to uh, do both?
Um, so this is very flattering, by the way. Thank you. But this is, I think this is a really important observation. Um, just kind of about the nature of engineering. So I'll answer your question in a second, but I kind of want to talk about the broad space real first, right? So in every area of engineering, you can kind of think of it in like layers of specificity. I think of this as almost like the Google Earth view of a problem space, right? You can zoom out and see all of the continents and like, understand it at that level, and then zoom all the way in and see the electrons and the NAND gates and, the power specs and all that stuff. So, and then everything in between. Um, when you're problem solving, in an engineering context, it's really, really important to be able to hit that right level of zoom. Whether you, and this is true both for sort of solving individual problems and figuring out like what's the level at which I need to kind of do this, right? If you're trying to like make the button be like blue rather than green on the web page, don't go start talking about cache lines and like eviction and sort of pipeline performance and things like that. Like it doesn't matter, right? Just like change the CSS and be done with it. So find the right like level of zoom that matters for your problem. Find the right level of zoom that matters for your audience, right? Like you're talking to people and you're speaking in terms of like, really, really low level stuff and syscalls and all this stuff. That's not useful if like they're just trying to get some business logic to fit together, right? So like, you know, being able to kind of move up and down the layers of Zoom, like press plus, press minus, and like get to the right bits and like do that freely and connect that together, that is a really, really, really important skill. Like that's the definition of being able to be a broad engineer. So how do I do it? I think everybody has their own method for this, but I actually think about things in terms of functional programming. I really, really do.
Tell me more.
It's so functional programming has this neat idea inside of it, which is local reasoning, right? So like when you look at a small piece of code, you can sort of understand that code in isolation because everything in it is pure, like everything is referentially transparent. So even if the thing that code is doing is composing effects, and even if the thing that's underneath that code, maybe it's delegating down to like very, very broad things, like you can reason about it in isolation. You can like manipulate the parts like locally, right? Um, the underappreciated aspect of that is it's recursive, right? So when you put these things together, like my local bit that I was just talking about, well, that's inside a function, and then I'm probably calling that function inside some other function, which is also composed of some local bits, and I don't need to go back down to that lower level thing to like understand the big thing. Well, that sounds a lot like my layers of Zoom, right? So it's when I go through an organization and I think about your different services and your different data pipelines, if I think about your different teams and your orgs and your business verticals and like, whatever, um, I am genuinely mapping that in my mind the same way that I map going through a very large code base where I started from main and then I sort of like, now I see how your modules are knitted together and what flavor of dependency injection you're doing. And like this gets passed to that one and here's this lifecycle. And okay, I looked at this function. Now I'm going to go down into those implementations and look at those functions and finally work my way all the way down to the lowest level where you're like calling out to some libraries or calling out to the kernel or whatever it is you happen to be doing. That's the same part of my brain. So really, I think it was the realization somewhere along the line that the skill that I had been building for so long to understand a large and complex code base and break that apart and work down, and then evolve a large and complex code base in a way that that skill was applicable, right? That it was easy to start from a high level and work your way down, which basically means do it in a functional style, right? That's the best way to do it. Make a program composable. Um, at some point I realized, well, I can just do that with an organization as well. I can do that with data pipelines and services and systems. And so I genuinely think of things in terms of functions. I really, really, really do.
How does your open source work come into play while developing these skills? I'm curious because you've invested quite a bit of time developing a large chunk of the major libraries in the Scala ecosystem, and I was curious to understand how that work influenced the growth of these skills that you were discussing.
Um, in, I think, a couple of important ways. So one of them is that working in open source has really made me think a lot about framework design and about emergent consequences of framework design, like how are people going to use it? What kinds of patterns am I trying to encourage or disallow, or all that type of stuff. So you think about API design, you think about sort of framework concepts and verbs and atoms and like all that type of stuff. Um, so that's been a big part of it, is like you get very comfortable kind of in that space. Open source also by by necessity, right? Like the distribution mechanism is very different. Like things tend to be a lot more modularized because you have these repos that kind of exist in the ecosystem, right? It's not like all big one mono repo tree where like people are pulling in fragments of source code everywhere. Like it's very, very different from that. So that in turn has its own implications. Um, you get to be very patient when you're working in open source. Like open source is so strange because you do something and you're very excited about it, and that's why you're doing it, right? And you sort of hammer out the code, and like maybe it's a totally revolutionary way of doing a thingy madoodle, right? And then you push it up on GitHub and you put it on Mastodon or Blue Sky or something like that, and you're just like, maybe if you do a conference talk and you're like, hey, I came up with this thing for doing this thing that you should be excited about it too. Like look at my function signatures are so pretty, and everyone ignores you, right? Or at least it feels like everyone ignores you because nothing really happens. Maybe you get 2 more stars on your repo. But what you realize is that like change takes time. And you can put something out there, and even if it's really, really important and really impactful, like people need time to metastasize that and right really, really kind of work it through the ecosystem, work it through the adoption curve. So there's a lot of entropy and sort of momentum, positive and negative in software, and that's true both publicly and privately. So you learn that lesson in open source very acutely, especially when you do it for a long time and you see things that are successful, like maybe Cat's Effect, and you see things that are unsuccessful, like maybe everything else I've ever done, right? Like I've got so many more failed projects than I have successful ones, believe me. So you learn that, but I think most importantly of all, you learn people. Because at the end of the day, like not only is all of software development just like people doing things and interacting with each other, but like open source is a very distilled version of that. Like it's an almost anarchic version of it because no manager is there to adjudicate something. Like nobody's going to decide for you. It's just like you got to convince this other person, like please adopt my thingy. Um, and so you learn how to influence people broadly. You learn how people are going to react to things that you do technically, right? Like I made a change to IO that like looks like this, which means that people are going to sort of emotionally and also rationally act in this way, and that's going to lead to these effects. You kind of learn to connect those two things together very, very, very closely. And then they become kind of parasympathetic, right? Like you do things in technology, it influences the people. You do things in the people, you bring it back to the technology. That's a very, very important skill.
If you were to start a fresh, new, foundational open source project from scratch, and you wanted to make it successful. Maybe if you had the idea of Cat's Effect, you have this giant light bulb, you have all the context in your head, you have all the knowledge that you have acquired through lots of experience, lots of experimentation and stuff. You have it, you've written down. How would you start a project like Cat's Effect from scratch? And what pillars or what aspects of it would you focus on to make it a sustainable OSS project?
Yeah, this is a very good question. I'm going to generalize it. Um, so all technology is contextual. And that's true for software. It's true for banging rocks together. Like everything is in context. I think as technologists, we have a tendency to kind of look at technology and software and frameworks and hardware as if it was like some sort of like civilization tree, right? Like the M5 is better than the M4, which was better than the M3. Like, so clearly we should use that. And like, this version of Cat's Effect is better than this other version. Cat's Effect is better than Scala Z task, which it predated it. So there's a linear progression in our mind, and really, technology isn't like that. Not at all. Um, I think a lot about how in I believe it was the 12th century, the Chinese developed the steam engine. And um, there's a lot of things, by the way, that go into developing a steam engine. Like it's not just like putting some water in a kettle or something like that. Like you need various forms of metallurgy and casting, so you can actually like have a chamber which can withstand very high pressures. Like coal is pretty important because you need to get very high temperatures. You need like control of all these different things, right? Um, and as Europeans and people of European ancestry, like we think about the steam engine as like, oh, this was the harbinger of the Industrial Revolution. Like development of that, like in the late 18th and early 19th centuries in England, that was so important. That catalyzed everything that followed, right? From that, you get the railroads, you get factories, you get you get the world we have today, right? So clearly, in the civilization tech tree, right, that's like the next step. And what happened in China? Well, they didn't do anything with it. Now, is that because the Chinese are worse at developing technology than the Europeans? No, clearly not. Like obviously not. So why didn't they do anything with it? Why didn't they see the potential? Well, we forget that when the steam engine was developed in England, it was developed within a context that had already partially industrialized. You had textile mills and like flour mills and other things that were using water power to like spin wheels at very, very high scales. You had railroads. People forget that the railroad came before the steam engine, but it did, and they were actually reasonably in heavy use, especially around like port facilities and some of these nascent factory facilities. That was happening in England before the steam engine. And then the steam engine comes in and is like, yeah, you've got your railroads. Well, we can replace the horses that are pulling your carts with like this iron thing madoodle. And like now your carts can be pulled much faster and more heavily laden. That's incrementalization, right? Like it's a context into which you introduce a technology that together unlocks a broader advancement. So when you're thinking about foundational libraries, you have to think about the context. When you think about any technology, you have to think about the context. And you have to be able to build incrementally on what you have to get to where you're trying to go. Now, maybe where you're trying to go is a giant, giant paradigm shift from where you are right now. Most of the time, that's not going to work, by the way, even if it's a brilliant idea, but like maybe it's worth it. And so if you really want to go that giant paradigm shift to some sort of unicorn tomorrow, you have to like really understand that vision of the future, be somewhat flexible on it because it's going to change, right? Always in motion. And then you have to work your way back to like the present and build nice, neat little stair steps that take you from here to there. And you have to do that. And then in open source in particular, those stair steps have to like connect to all of the other people building stairs around you. And they're going off towards their own unicorn tomorrow. So it really helps if like they're all building stairs in the same direction. So story time, like one of the things that happened right at the beginning of Cat's Effect actually is like a bunch of us actually got into like a closet at I think it was an NE Scholar or something like that, and we talked about Cat's Effect. We talked about like, well, this is the gap in the ecosystem, and we coordinated about like, well, this is what we want to do about that gap, and here's how we're going to go about it. Here's the pieces we need right now. Maybe tomorrow we'll need different things, but this is what we're going to do. And we all kind of like laid out how everything was going to connect together. You have to do that. Like you have to be incremental. You have to be sympathetic with the ecosystem. You have to build consensus. Most of that's a human thing, not a technology thing.
That's a very interesting answer because what I was expecting was okay, so I have the code. I'm going to push it and then I'm going to do a conference talk and then I'm going to talk to such and such people and then I'm going to get such and such contributors and then maybe some company sponsors me and then I'll get a flywheel spinning and then the project becomes sustainable. But this is a very, very interesting way to look at it because you can only make a project sustainable. So what I'm hearing from you is that most of the success of, in particular for this particular question, an open source project, boils down to whatever environment the open source project is thrown into. It's in much the same way as, I don't know, habits are easier to stick if you can, make an environment in your home or in wherever you're living conducive to that habit, which then compounds and then builds whatever you want to build for yourself. So I wanted to follow up on that and ask you about the current context. What is the current context, and maybe narrow it down to the current context of the Scala ecosystem? What is it fruitful for? What do you think the current context of the Scala ecosystem would be very conducive towards? For example, and you can take this question in any direction you like. Is there a time? Is this a time for a killer web framework for Scala? Is it worth it? Is there something else that would land in a fruitful environment? How do you think about this?
This is a very, very good question. Um, so let's talk about what Scala is really good at first, right? So, and it's also an interesting topic of conversation, like how it got to be good at these things, but like we're just talking about the now right now. So Scala is absolutely best at the backend network services space. And I will cop, by the way, to the fact that I have a little bit of a bias on that, which is this is the space that I see the most of because, not only does my job in this, but also like the frameworks that I maintain primarily are living in this type of world. So I don't write a lot of like DevOps tooling or something like that. Um, if you believe the sort of the surveys that have gone out, like JetBrains and like Scala Center's done stuff like this, and there's been a few surveys over the years that kind of look at this space. Most people using Scala are doing services with it, usually like RESTful services or gRPC. There's a large contingent who are also doing DevOps tooling, but like really it's that type of thing. And then you've got a bunch of people who are doing data stuff, right? Especially built on top of Spark. Um, the Spark stuff is kind of gone now because like all of those people really wanted to do it in Python anyway, and now you can. So, that's just kind of a thing. The DevOps tooling, I think in a sense, that's getting eaten alive by like these things that do support static linking, which is really, really important in a DevOps environment. So it kind of brings you back to this services environment where the JVM is really, really, really good, aside from the containerization issues that we kind of talked about. It's just really, really good at like dealing with stateful, like heavy services, especially long-lived ones. Um, the Java ecosystem is very robust and mature in this space, and the Scala ecosystem in particular is a really, really good flavor of it. So it's very easy to do extremely high scale backend services in Scala, and it's also easy to do really low scale ones in Scala. Like it's that type of thing. It's just super good at that. So when you think about, how do we build on top of that technologically? Um, there's a couple of areas that my head tends to go. One of them is like we can kind of keep polishing it, right? It's already fairly mature, but like there's loads of ways that we can kind of make it better. And this gets you to things like performance, it gets you to things like safety, it gets you to things like, you know, let's let's improve the stability of like our database libraries or our HTTP libraries or something like that, like ergonomics and such documentation. Okay, great. Like you're kind of polishing something. But if you want to do something like really, really new, how do you grow off of this? And I think this is maybe I'm going to sound like I'm beating a dead horse, but this is exactly why I start thinking about deployment environments. Because things like AWS Lambda, things like containerization, things like platform access and hardware specificity, right? Because these are things that are not well served right now. Like one of the challenges with Scala and one of the challenges with the space that Scala is really good at today is that's also a space which, not by coincidence, is very, very mature. Like you don't really need to write a new HTTP framework for Scala. Like you can, it's kind of fun, but like it's going to take you a very long time to get to be as good as like some of the players that are out there right now. And even if you have an idea that's better, it's still going to take you a really long time. And then there's a lot of entropy involved in like actually moving people over to like adopt your thing. So it's really hard to kind of compete with the incumbency in that regard because it's so polished and mature. Um, but there are things that the incumbency is still fairly bad at, partially because of historical accident. So the AWS Lambda thing, the containerization thing, startup times and auto scaling, memory footprints, short-lived services, really not very good, and bespoke hardware access and bespoke system access, right? GPUs really, really a terrible story on the JVM. So, you know, where you go with that is kind of, another question, right? Like, what would it actually look like to be better? And is that just a limitation of Java? Like, do we have to go to Scala Native? I think we do, but like, you see kind of where I'm going at it. I think if I were introducing a new foundational Scala framework today, or if I were trying to attack a space in Scala, it probably would be somewhere around there. Like, because I feel like that's the thing that's incremental with respect to the thing that Scala is very good at now. So it has built-in adoptions, like there's a very obvious pathway to these things. It solves real problems, um, but it's also a space that's very poorly addressed. Okay, I apologize. My boss is poking me. You're gonna have to give me a split second.
No problem. We're going to cut this out. A bit of time later. All right. So before the little break, we were discussing about the space that Scala can uniquely fill, and we were discussing about web frameworks and the fact that the space is very crowded and the incumbents are very hard to compete with. But you mentioned something that piqued my interest, which is a space that has been uh, insufficiently explored. Can you tell us more about that?
Yeah, so I feel like the space is best typified today by Unison. So Unison is a number of things simultaneously, which makes it difficult to talk about. It's a language, which is very Haskell-like in some ways. It's built by a lot of folks who built a lot of the things in Scala, most notably FS2 and things like that. Um, it is it is a runtime, so this kind of gets into like more of the weeds, but there's kind of two different styles of uh, sort of runtime system that you can use for languages. One of them, which we sort of tend to use today, is sort of textual or like encoded. The other one is an image runtime. This is very, very, very uncommon, but it was pioneered by Smalltalk, and there's a number of other systems that have experimented with it. Unison does an image-based runtime. There's a couple of important things that come out of that. And then the other thing that Unison is sort of a cloud platform and sort of a hosted thing that they have, a version of it that you can install yourself now. So it's all of these things kind of put together. That's not the thing that I want to take inspiration from, though. The thing I want to take inspiration from is the observation they made that the application is not just the thing which is running within a single Lambda or a single pod or a single VM or something like that. It's not the process. The application, for most people, especially people doing distributed systems, by definition, the application is the whole thing, right? The whole deployable. And anybody who has done cloud deployments at all understands that that is a much more complex thing to talk about. We basically jump from this land where we have really nice tooling and we have languages and type systems and unit tests and like documentation and LSPs and things like that. We jump from that universe into like absolute YOLO town craziness with Terraform and CloudFormation and like DevOps that only half works and kubectl and like just things are so miserable and there's this terrible continuum from that into operationalization and operational tooling and monitoring and things like that, which is also a really awful space. And it's just this very discombobulated mess. So like if you want to actually take your source code that you have in your editor buffer and get that all the way to your user's eyeballs, the last mile of that per se is actually really difficult. Now, this is kind of AWS Lambda's whole pitch is that, okay, we'll make it really easy for like these super trivial cases, but Lambda has some other trade-offs and it doesn't make everything easy, right? You're still going to be off like manually pressing buttons in the AWS console to get RDS instances and like provision your VPC and like, and then you're just like, what even is a VPC? Like just all of these are sort of incidental complexities. And to me, that's one of the most revolutionary things about Unison is like they looked at that space and they were like, these are all incidental complexities. These are all stupid. It should all be in one place. And we're not going to accept that it has to be like this. right? So rather than spending half of our time writing code in a pleasant language and the other half writing code in YAML, let's just write code in our pleasant language all of the time. I'm paraphrasing Paul at this point, but I think he would approve of the way that I'm delivering this. So now Unison has to do a number of very specific things in order to achieve this goal to the extent that they achieve it, and they do achieve it quite well. But I think that we could probably do more than we are doing in this space. So the context for your question originally, I think, if memory serves, is like, what is sort of an open area of innovation in the Scala ecosystem? And I think this is really it. Like Scala is already, it's an incredibly good language. The tooling is better than people think it is because most people don't have a point of reference, so they don't compare it to other languages, which are a ghetto hellscape. Like, you know, the ecosystem is very, very mature. It's well positioned in adoption as far as backend network services go. So it's like right bang in the middle of this. If I were starting a new foundational layer of the ecosystem today, that is what I would focus on, was really the DevOps space. Like DevOps deployments, deployment orchestration, things of that nature. I would be trying to sort of be compatible and composable with Terraform and other major systems in this space, Helm, rather than replacing them. But I would want to make it so that at least for the 80% scenario where people are deploying a backend service and they're auto-scaling it in Kubernetes and they've got some database and they've got a load balancer and then blah, right? Like the blue-green deployments, all this stuff. That should be something that you can do kind of within your language, and you should control it within Scala CLI, and you should have this nice sort of uniform playground where things kind of function. You're going to hit edges where it's going to be difficult to do that type of thing because of the nature of the JVM, the nature of textual runtimes, like et cetera, et cetera. But we can do so much better than we have done. I just want to be so super clear. It is a very, very, very hard space, but it's a very impactful one. And when you think about things that are selling points to engineering organizations, this is one of those things that starts to rise up to that point where people might choose Scala for this reason. Like if we really had a solution in this space which was mature and did really well, like that's a very, very compelling pitch. Like, hey, all that like that time that you spend, that money that you spend on folks, basically just like this is the one guy who understands Kubernetes, and like our bus factor is one on like our whole org. Like everybody's got that one guy who understands Kubernetes. Well, okay, maybe you don't have to have that anymore. Like that's super compelling. Like this is really, really, really compelling.
I have a bunch of follow-ups to this one. I have three. I'm just going to pick one.
Go for it.
How do you start with, let's say, as a single developer, given the fact that the Scala foundational tooling space is usually very resource constrained? And by this, I mean there's one person working on SBT, one person working on Scala CLI, one person working on Scala JS, one person working on Scala Native,
Mhm.
half a person actually working on Scala Native because Wojciech is actually working on many things.
But he's like
And
10 people, so like, it's the coefficients on both sides.
right, but you get my point, right? So what would you start with for something that feels very foundational in a hard space with many branching points that you have to
Yeah.
just pinpoint nail hit? How would you start this? I mean, if you had, okay, let me give you like a very specific. If you had 3 months or 6 months to
Mhm.
work on something that could deliver some tangible value, what would you focus on?
Um, it would depend greatly on like, so ideally this would happen within the context of me, myself, or my team feeling some acute pain in this. And then, I have some expertise, I have some place that I can like work on it in deployment. It's not happening in a vacuum. I'm scratching my own itch. Um, and then I would circumscribe what I'm trying to do in those 3 months, basically, in the light of those types of requirements. So, okay, I'm deploying on AWS. I'm using Kubernetes, but I'm using it in this particular configuration. I'm using not RDS, but I'm using Aurora, right? Like I'm just picking stuff, right? I'm only deploying in a single region and one availability zone. those types of things. Like start sort of walking it down. Um, and then I would try to kind of nail that, but I would nail it with a vision for here's what it would be in a more general sense. So like I've been doing DevOps for a very, very long time. So I've seen very, very large and complex systems. I've seen very simple systems. So I know that like if I want to solve the very complex case, I have to think about all these other things. So like maybe I would try to think about it in that realm, but I would really try to nail just that first bit. This kind of goes back to what we were talking about, previously, where it was just like incrementality is king, right? Like you have to compose with what you have, you have to be incremental, you have to kind of get that POC through. So I think that's what I would focus on doing, is like really nailing that very, very basic case. And a lot of other things would kind of fall out of scope. Um, this is it doesn't solve the sort of resource constrained problem in the broader Scala ecosystem, but that's not a problem that I can solve. And it's also sort of like in some sense tangential, right? Like a lot of things like Scala.js, Cat's Effect, like things like that, SPT even, these are very mature tools. And so maintaining them is kind of almost a different skill set than like getting something off the ground in the first place. And different people tend to be interested in them.
That's fair.
So,
Okay.
yeah.
Um, Follow-up number two.
Mhm.
What would you, I mean, how would you estimate success for something like this, given the fact that Unison is fighting in a crowded space, and it needs to convince a lot of people to use that full stack? It's not actually a stack, it's a whole blob of things,
Mhm.
but it's packaged in one package.
Yeah.
And it has to convince a lot of people and organizations and teams to pick something that hasn't really been done before in that particular style. And I'm sensing what you're suggesting is in that style as well. How would you shoot for success um, with something like that?
Um, Precisely by not doing what Unison did. So Unison invented a new language, which is already a giant bar. Like it sort of has a new runtime, which is like doubles that bar. Like this, that, and the other thing. I would um, I would work with the existing Scala ecosystem. I would work with the JVM, so I wouldn't be kind of creating this whole new thing. It essentially this would be almost a meta framework on top of what we already have. Is like kind of the space that I'm thinking about. Um, I would probably assume some very specific things. Like I'd probably assume Scala CLI and SBT, like, that type of thing. But basically work, again, this kind of comes back to my like assume you're solving your own pain point and then kind of generalize from there. And then what I would define success to be is like, can we get something that's like a really, really smooth experience for people that are like right in bang in the heart of that like problem space? And then get that to be something that a few folks adopt. Can we make that something that composes with their existing deployment orchestration system to the extent that they have one? Teams that have really, really good deployment orchestration probably are not interested in this because that only happens when you've got some infra group that's like solving the problem for you. So it's folks that are kind of fighting the cloud formation fight by themselves that are going to be interested in this. And I think that get some adoption in that, and that would be success. Like, and then you can kind of roll from there and get people start incrementally expanding the space of what you're capable of doing, and try to do that without reinventing Terraform.
That's that's a challenge, but I think it's a challenge worth taking on. Which brings me to follow up number three, which is the fact that as far as my conversations with other people in the Scala space go, Haoyi Lee is working on Mill as a build tool that wants to be this very general build tool that has a number of optimizations and aggressive caching and whatnot.
Mhm.
But deeper than that, he wants to use Mill to apparently fill at least part of the space that you're describing. Do you see Mill or uh, a build tool like Mill as a starting point to um, trying to hit that problem space?
Maybe. You definitely have to be in that type of meta layer. So that was kind of why I called out like assume Scala CLI, assume SBT. If you want to assume Mill instead, go for it, right? Like you basically have to assume something there. Um, I'm basically not aware too closely of a lot of the efforts that have been going on with Mill in general. I guess part of part of my thinking on that front, um, I've seen a lot of build tools come and go. Um, and a lot of the things that Mill is doing now, ironically, are things that SBT used to do and then sort of changed for various reasons. Now, everybody picks different trade-offs, right? And like Mill is picking, has a slightly different set of values, so it's probably going to evolve in a different direction. But like you basically, in terms of build tools, you basically always end up being some corrupted version of Bazel or some like very, very bespoke thing like Cargo or Go, or, some like kind of beautiful thing that like does a bunch of stuff, but then nobody understands it, like SBT. Um, so I'm curious to see kind of like how Mill evolves in that and how it sort of goes. I feel like in this space, Haoyi tends to have really good taste, like this type of tooling. I think he has really good taste. So yeah, if he's trying to whack this problem, I'm actually pretty optimistic about it.
Nice. I want to be respectful of your time, so I would like to move us towards wrapping this conversation. So I had a few rapid fire questions for you.
Mhm.
First would be, what does the way that I originally phrased this was, what does a day in the life of Daniel looks like? But I would like to ask a different version of that, which is, how does a quarter of your life look like? A quarter being like a couple of months, 2, 3
Right.
months.
Um,
'Cause I'm
uh,
pretty sure that no 2 days are quite alike. So
every day is different. I mean, over the course of a quarter, there's usually a lot of, I mean, there's always an enormous amount of meeting people, sort of understanding their problem space. There's usually over the course of a quarter, I'm kind of focused on maybe 5 or 6 kind of quadrants at once. Um, and within that, there's going to be a lot of progress made over the course of a quarter because teams work pretty fast. But at the same time, they're never going to do quite what I wish they would do. So, usually along the line, I'm sort of telling them like, hey, your life will be easier if you do this. And they do like, if I'm lucky, 70% of that, but more likely 30%, right? And then, we get to the end of it and I'm like, cool, call that success, right? Um, I think I know it's a rapid fire, so I'll end with a quick thought, which is that there's never as much progress made as I would like on the grander vision. And really, like, engineers in general, like ICs, are very low thrust, high impulse actors. Like the things that we do, we see results on them over a very long period of time as you sort of point in the direction and unfurl the solar sail and be consistent about it. But over the course of a week or a month or a quarter, you're not going to see very much, and you just have to be okay with that.
speaking of these sort of general tips, how do you maintain your learning curve steep? Because we were discussing earlier about your position, which is pretty high up in the IC hierarchy. How does one keep a learning curve very steep across many years so that they can get to the level that, for example, you have?
I think the most important thing is being humble, which is something that I very frequently fail at. Um, but I think being willing to ask questions, being willing to like look foolish in public is a very, very, very important meta skill on that. Like I will go into meetings with like hundreds of people, and then like if I don't understand what's going on, I will say like, hey, this doesn't make any sense to me. I don't understand. Um, and if you're not willing to do that, you're not going to learn. And the problem is that like as you get more and more senior, there's a self-perception that comes from imposter syndrome where you feel like you're not allowed to do that because then people will realize, oh, you're not actually as smart as they thought that you were, right? But like you've got to be humble enough and sort of, I guess, confident enough to just put egg on your face and be like, I don't know what this means. Can you please explain it to me like I'm 5? Like, and just be always willing to do that. And I think between that and remaining constantly curious and constantly dissatisfied, like you have to do those two things. And if you sort of maintain all of that, then the rest will take care of itself. Like I've got a billion side projects that I'm doing because I'm curious and ask a billion questions and I learn stuff from that.
Any particular reading that you think is really, really indispensable that you think everybody should read. It could be a technical book or something non-technical. If you say Lord of the Rings is great for computer scientists, or that counts too.
Yeah. Well, I like Children of Time, so you should read that. But this maybe is not indispensable. It's just really good reading. Um, I think the I'm gonna I think I can't point to a specific tome which covers this, but reading a lot about formal logic is really, really helpful. Um, I think almost daily about Scholomization. So if you don't know what that is, you should look it up, and not just the compiler error, but like actually the concept behind it. Um, and there's sort of like a deep rabbit hole in there with like the work of Curry, and the work of Church, and like a lot of Gödel, like a lot of that stuff that happened around that time period was very, very influential. Just deep, deep, deep thoughts about computation. Um, all of that really matters.
Thank you. Thank you so much for uh, all of this and for making the time to chat with me. It's been a real pleasure, and I'm a really big fan of your work. Before we wrap up, is there any thought or any tip or anything that you would like to send to my audience before we wrap up? My audience being, at the moment of this recording, mostly Scala developers. So
Um, so first off, thank you. I'm also a big fan. So the thank you for having me. So I guess that's the first thing I would say to the audience is thank you for listening. But I think secondly, I would say appreciate what you have. Like I've spent a lot of time over the past couple of years not in the Scala ecosystem and not in the JVM ecosystem, and it's amazing how crude many things are in the outside world. Like we have built a really, really nice little paradise for ourselves. Like there's many things wrong with it, but there's a lot of that's really, really good about Scala. So yeah,
that's a very, very good thing to wrap with. Daniel, I really appreciate you making the time, and I will leave everything in the description of the video. And until next time, guys, thank you so much for listening.
thank you.